Welcome to this fourth lecture of the short course on machine learning in communications. We will be continuing our discussion on statistical estimation and its role in machine learning, which this is a topic we started in the previous lecture and is basically the main theme of our second module. Today, we are going to focus on the classification problem. As you can perhaps all imagine, classification plays a significant role in communications. There are many problems that benefit from this classification idea. The prime example here, which is also related to the examples that we have come across in the past few lectures, would be a decoding problem in digital communication system, right? So you have a received signal and you want to attach a label to that received signal. And that label is, for example, just a constellation point from the constellation that you've been using, right? So that is the decoding process, and you can also equivalently think of that as a classification problem, where you're trying to classify to which bits or to which symbols is your received signal mapping, right? So I thought it would be good to dedicate a very short lecture on specifically on classification to introduce some of the basic ideas related to it. So the specific topics that we are going to cover are the idea of a Bayes classifier, which will be related to this regression function calculation that we did in the very first lecture. Then we'll see that Bayes classifier, although pretty interesting, is not something we can directly work with. So we'll introduce the idea of a naive Bayes classifier. I'll explain in detail why this is naive. Then we will look at the idea of logistic regression. It's actually not regression, it's actually a classification scheme. So a bit of a misnomer here. And we'll also look at its underlying generative model in the same way as we did for regression in the previous lecture. Right. Then we'll conclude this lecture by discussing some interesting connections between logistic regression and naive Bayes classifier. And these connections are interesting because these classification schemes, logistic regression and naive Bayes, are conceptually somewhat different. You'll see what I mean by that when I explain them. But at the end of the day, you can show that they are doing roughly the same thing, of course, under very specific assumptions, which we'll make and make very clear when we derive this at the end. So let's begin with the idea of a Bayes classifier, right? What do we mean by Bayes classifier? So before we go there, let's recall what we did in lecture 1, right? This idea of a regression function, as you might recall, right? The idea of a regression function, right? So the problem I posed there was, it's going to be very similar to what we are going to assume now. So the problem was you have features X and labels or outputs Y, which are sampled from a joint distribution PXY, right? Let's assume that your label, right, estimated label is some H of X. Right? Because your estimated label is nothing but a mapping, right, from your features onto the output. So Y hat is essentially just the mapping, and we label that, or we define that mapping as H of X. And then we said that, okay, let's assume a squared loss function. So this was your squared loss function. And we said that which function H will minimize the expected squared loss, right? And we showed, and it was quite straightforward actually, to show that the function that minimizes expected squared loss is nothing but the conditional expectation defined here. So hx is expectation of y given x equals to x. And if you think about it, some of the learning algorithms like k nearest neighbor, right, the simple ones, they're basically just trying to do this directly. Right? I made a remark on that when we discussed regression function as well. Now, the question I'm going to ask now is, can we do a similar calculation for the classification case? right? As we did before, we of course have to assume a specific loss function, and the loss function I'm going to assume for this calculation is a 0, 1 loss model. So what we are going to derive with this is a Bayes classifier for this specific loss function. Okay, so everything we are going to do next is basically under this assumption of 0, 1 loss. Okay. So as before, we are going to assume that your features and outputs X and Y, right, are labeled from the joint distribution PXY, and I'm going to consider a general classification problem where your label can take one of the key values, right? So Y is taking values from this set. There are going to be some problems, some derivations today where I may confine Y to binary values, so I'll make that clear whenever needed. All right. So now we are interested in finding a function g, right? Similar to this function h, I'm just defining a function g, right, which is a mapping from your feature space onto the labels, right? So g goes from whatever your feature space might be onto these discrete values. Okay. So which means that now I can write my loss function, right? I can write my loss function as L, Y. I can write this as say Y hat for now. And then this is nothing but L of Y GX, right? Because my estimate of Y is nothing but GX. That is the mapping I'm interested in knowing. So this is my expected loss, similar to the regression problem we did before. So this is my expected loss, right? Expectation is over the joint distribution of X and Y. Now, as we did before, I'm going to apply Tower rule here, and I'm going to first take the expectation with respect to, so Y given X, right? So this is conditional expectation over Y given X, and your expectation with respect to X is sitting outside, okay? And you get a summation here when you expand that expectation because Y is a discrete variable, right? When you just solve for that expectation, it just gives you a summation. And one thing to note here, let me see if I, so one thing to note here is the following. So my loss function is 0, 1, which means, right, so I have these k terms in this summation, and for each term, L can either be 0 or 1, right? And one of these terms is going to correspond to the correct value of the estimate, and all other terms are going to correspond to the incorrect estimates, right? So this loss, in other words, L of Y GX, right? It is going to be equal to 0 when Y is equals to GX. When I have made the correct estimate, right, then the loss is 0. Otherwise, loss is 1. Okay. So what does this mean now? So you have this summation over the PMF, which is multiplied with this loss term, right? If this loss was 1 for all the terms, this is nothing but your summation over the PMF, but we know that there is going to be one term for which loss is 0, right? Which means you get a sum over PMF because the other terms are 1s, but without, but one of the terms in the PMFs would be missing. So you add and subtract that term, and what you eventually get is this. So this is again our expectation sitting outside. This one corresponds to the one that you get from the summation over the PMF. And this is the term that corresponds to the loss function, which was 0, right? Remember, loss function was 0 when Y was equal to GX. So this is the term corresponding to that, okay? So similar to what we did, and again, if this did not make sense, you can just write that, right? Just expand that summation and you will immediately see what I tried to describe. Now, as we did in case of the regression function, what we are going to do is, right, we are going to minimize this loss. We are going to minimize this term here. So I'm interested in this. I'm interested in argmin over G expected loss. Right? As before, we can do this pointwise, meaning I fix the value of X and then I determine this argmin. If I fix the value of X, what do I get? I basically get rid of this expectation because it is expectation over the distribution of X. So if I'm doing this minimization for a given X, then this expectation is not needed, which means this argmin over the expected loss basically reduces to argmin of negative of this probability term, which is argmax of this probability, right? So y hat, which is g hat x, so this is the function that I was after, that is nothing but argmax over this probability term, right? So written differently in a slightly different notation, which will be more illuminating, this is nothing but argmax over y, g of y, given X, right? Oh, so this is not G. Okay, let me just write this again. This is argmax over G, right? Or argmax over Y, P of Y, given X. So y hat, right? It's nothing but you're basically maximizing your posterior, right? So this is what we call a Bayes classifier. Right? So y hat is nothing but you take the posterior of the distribution P of y given X and take argmax over Y, right? You maximize the posterior. This is called a Bayes classifier. And the corresponding error that you make in this case, which is also the minimum error possible, right, for this loss function, is also called the Bayes error, right? Just some terminology here. And as was the case in the regression function, this is what a k nearest neighbor algorithm would try to do when you implement classification. Okay, so it has sort of some analogy to regression function in that sense. All right. So again, very quick summary, right? What we obtain is if you try to minimize your expected loss, where loss is defined as a 0-1 loss, then your calculation reduces to this argmax over a posterior, right? So you just try to maximize the posterior. Now, the question I would ask you at this point is, so are we done, right? And it would be a good idea actually to pause this video at this time, right? If you are watching this offline later, and just think about it. Are we done? And this will also help you determine if you're sort of getting the essence of the type of assumptions we are making, right, in developing these learning algorithms. Now, the answer obviously, right, is that not so fast, right? Since we don't have the true distribution, which is the key, we cannot implement the Bayes classifier directly. We know what is the right thing to do, but we cannot do that directly since we don't have the true distribution, which means we now need ways to estimate that distribution, which will be the topic of today's lecture. So we're going to look at a couple of ways of doing that. Okay. So there are two main approaches we will study. Naive Bayes approach, which is pretty much trying to do what we just saw, but under a specific approximation. Okay, so what it does is it will estimate the likelihood P of X given Y and the prior P of Y, and then apply Bayes rule to determine P of Y given X, right? And it is also a generative approach. It is also a generative approach, which we'll discuss in a minute. And there is a reason why this will be called naive. So there is a specific approximation which we'll discuss and also motivate why we need that approximation. Okay. So the second approach, which we will be discussing, is the logistic regression, right? So here we will directly estimate, or rather we'll sort of assume a model for this posterior, and then we'll try to do some calculations with it, right? And this is also called a discriminative approach. Now, the question for you is, why do we call the first approach generative, right? And likewise, the second approach discriminative. So the first approach, since you get both likelihood, P of x given y, and P of y, right? You can, in principle, also sample new data from your estimated distribution, because you can basically obtain the joint distribution. So you can create a new data set, if you will, from your new distribution. But if you get only P of y given x, right, then you don't have the complete information to sample a new data set. So in this case, there are going to be techniques, again, which we are not going to cover in this lecture, which don't even go into estimating this probability. They directly try to discriminate between the points, right? So that's why logistic regression lies in this discriminative approach, right? Because we can't really generate any data with it. So let's start with the generative approach. Okay. Okay. So first thing to understand is, right, we said that this naive Bayes approach is a generative approach. So the first thing that comes to mind is, why naive, right? So why to be naive? So let's try to understand this very quickly. And it will also motivate the assumption that we are making in naive Bayes. Let me write a couple of steps to quickly explain this. Consider a simple case where we have binary features, which means all xi's, right, will take values between from the set 0, 1 for all I, right? Let's say that again we have a discrete output, which means y belongs to this set 1, 2, so on up to k, right? So our goal now is to approximate two distributions. We need P of x given y and P of y. Note that this is a fairly, simple case because we are assuming binary features, right? In reality, you might have significantly more complicated cases where, for example, xi could be real values. Now, if we don't make any assumptions, how many parameters do we need to estimate these two distributions? Let's take a very quick look. I'm going to first look at this marginal, and then we'll look at this conditional, and we'll see why this conditional is an issue, okay? So I'm going to look at the marginal first, P of y equals to y, right? This is nothing but P1, right, when y is 1. I was using θ1 before, right, in the previous lecture, P2. So these P1, P2 are the parameters that I need to learn. This is y equals to 2, so on up to 1 minus equals to 1 to k minus 1 Pm y equals to k, right? I don't need to learn the parameter corresponding to the last term because I know all these parameters sum to 1. This implies that I need actually k minus 1 parameters for this distribution. I need to learn k minus 1 parameters, okay? So let's see now the second case, which is the joint distribution. So I'm interested in P of x given y. So this is nothing but P of x1 equals to x1, x2 equals to x2, so on up to xd equals to xd given y. Right? So this is the joint distribution that I'm interested in estimating. So let's just fix the value of y. Let's say we are doing this estimation for y equals to 1. Right? I'm interested in, say, P of x given y equals to 1. So if I look at the number of parameters that are required here, so we are going to need θ1 when x1 is 0, x2 is 0, so on up to xd is 0. I'm going to require θ2 when x1 is 0, x2 is 0, so on up to xd equals to 1. And then I'm going to need theta of 2 raised to power d when x1 is 1, right? So all possible values that x1 so on up to xt can take, so that will determine the number of parameters I need. So this is x1 equals to 1, x2 equals to 1, so on up to xd equals to 1, right? Again, all these thetas have to be equal to 1 because this is a distribution, and hence the number of parameters that we need for a given value of y, right? For a given value of y are 2 raised to power d minus 1, right? Since y can take k values, so what we get, the total number of parameters we need to learn is 2 raised to power d minus 1 times k. And since d is the number of features, d can be oftentimes pretty large. So this starts becoming a hopeless problem, right? This is a very difficult problem. You have just too many parameters to learn, and it's not going to remain tractable. So that is where naive assumption comes into the picture, naive Bayes. And I think some of you can probably guess that right away, right? If learning this joint distribution is difficult, what can we do to make it easy or make it at least doable, right? So the obvious thing we can do is to assume conditional independence, right? We assume that given your label, your features or inputs are conditionally independent, right? So this is what a naive Bayes classifier, right? The assumption that naive Bayes makes. Now you can argue, right? I mean, is this a reasonable assumption? It really depends on the problem, the data set, right, that you are working with. It may or may not be reasonable. It all really depends on the nature of the data, right? If it exhibits independence or not. But it is my understanding that naive Bayes has been used quite extensively. Right. Now, if you now think about estimating this distribution, this is a far easier problem, right? So what you get is in this joint distribution term, which was the concern for us, right? When we wrote without this assumption, when we tried to estimate this distribution, this now is just a product of these simpler conditional distributions, P of x equals to I, conditioned on y equals to y. Right. Now, the problem reduces to estimating these distributions, and that's not very difficult to do because we already assumed that x was a binary random variable, right? So since x is binary, you just need one parameter to estimate this distribution here. So for every given y, you just need one parameter to estimate this term of the distribution, right? So for each y, you have d terms here in this product. You need one parameter for each of these terms, which means you need a total of d parameters to estimate this product, right? Or this joint distribution under this assumption. And since you have a total of y can take one of the k values, the total number of parameters you need to estimate is what? K times d. Far, far, far easier problem than estimating 2 raised to power d minus 1 times k, right? Okay. So the real reason I introduced this naive Bayes was, of course, to first provide some intuition. If we have this nice form of Bayes classifier, right? Why do we care about the other classification techniques? Why not to just implement that? And secondly, we'll see that it has a very interesting connection with logistic regression, right? So that is something we will discuss in a few slides. But before that, let's introduce this idea of logistic regression very quickly. You can think of logistic regression as the counterpart of linear regression for classification. It has a very similar feel, as we'll see. Now, for logistic regression, we consider this problem setting where your features are continuous, right? So your d features coming from your feature vector is coming from Rd. Your output is binary, y takes a value 0 to 1. So now the distribution of output conditioned on the features vector, right? Y conditioned on X is nothing but a Bernoulli random variable because it's a binary random. Y is binary, which means you can just model that as a coin toss. What you have to be careful here is your conditioning on X, which sort of means that you are selecting a coin based on the value of X. So Y given X is Bernoulli with the parameter theta X. Okay. Now, the objective is to characterize Py given X, right? Which means that we basically need to estimate this parameter theta X for every X. So the problem, we started with this distribution, right? Then we now have a model for this distribution, which is Bernoulli theta X, and the problem reduces to estimating the parameter of the distribution, which is theta X, right? And we'll see slowly how this connects to then approximating a function. So this is what we want. Right now, the first question, let me actually go to the previous slide just to create some space. The first question you could ask is, right, and we did something similar in the regression discussion we had in the previous lecture. So will this work? Can I just consider theta X to be some linear function of my features, right? I mean, this could be first obvious thing, right, that comes to mind. Sure, you might immediately realize that it's not going to work because this is not confined between 0 and 1, because P of theta X at the end of the day is a distribution, right? So you have to confine that between 0 to 1. But let's say that we still want to apply something like this. Let's see the type of problems we will face, and this will also give you some intuition as to what the classifier will be trying to do, right? Let's say that we have Y here, X here, some data points here corresponding to Y equal to 0. Then you have some data points corresponding to Y equals to 1 here. Right now, ideally, right, if you have a good classifier, you need some type of a separation here where you say that, you know what, if I lie to the right of this line, then I'm going to say that right, so Y hat, let's say, is 1. If I lie to the left of this line, I'm going to say that Y hat is 0, right? Fairly reasonable thing. But if I try to just use this theta X equal to beta transpose times X, right? Just sort of a linear estimate. What I'm going to get is a line that passes through this data, something like this. Right? It just doesn't really make much sense. So what I need to do is then I need to, as we identified before, right? So I need to somehow come up with a model that preserves the fact that theta X has to lie between 0 to 1, right? So I'm going to then introduce one such model, which is using a sigmoid function. If you haven't come across this before, right, this choice might seem very arbitrary, but through this remaining few slides, I'll actually try to convince you that this is a pretty good choice. And also this connection that we'll make with naive Bayes will also provide some additional intuition, right? But first, just some mechanics of what this sigmoid function is really doing, right? So let me just go to this page very quickly. So what sigmoid function is, sigmoid, which is sigma of z. This function is nothing but 1 over 1 plus e raised to power minus c, right? If you sketch this function, this is nothing but you have a z here, you have a sigma z here. So when z is very small, right, this decaying exponential is going to, for z tending to minus infinity, this is going to be infinity. So you get a very small value of the sigmoid. So your sigmoid starts here. And when z tends to infinity, this decaying exponential goes to 0. So you approach a 1. right? And this IPD will be 1/2. Yeah, this value is 1/2. So you can see that for any input value of Z, right, you get a value between 0 to 1. And this is sort of what we needed, right? So the assumption now that I'm going to make is Y conditioned on X is being sampled from Bernoulli theta X, right? So this is my model, and we already established that. Now the question is, how do we model theta X? And I'm going to say that theta X is nothing but sigma beta transpose X. So I pass this beta transpose X, right? Instead of using that directly, I pass that through a sigmoid. And now it starts making a lot of sense. Now, this is a model that is the generative model for the logistic regression. And the reason we call this logistic regression is because the sigmoid function is also called a logistic function. And but at the end of the day, keep in mind that this is a classification technique, right? It will be clear from our discussion. All right. So just to recollect, this is where we are right now. Y conditioned on X is Bernoulli, right? With theta X modeled as sigma beta transpose X. Okay. Now, once you make that assumption, right, then you can write your posterior directly, because you have already made an assumption about its form. So probability of Y equals to 1 given X is nothing but this term here, right? Just a sigmoid where you have the argument of that sigmoid is beta transpose X. And similarly, probability of Y equals to 0 given X is nothing but 1 minus of theta X hat. The theta X hat corresponds to probability of Y equals to 1. So you get this term here. Right? Quite straightforward. You can just write these on your own if you want. Okay, so something interesting happens here. So see, we started with a distribution model, and now we have reduced this problem to estimation of parameters beta from the data, right? So slowly we are going to this sort of a function approximation type of a viewpoint. Okay. Now for prediction, right? So you might ask, okay, we have this model, and I give you a input X, right? How do I determine whether that input X corresponds to Y equals to 1 or Y equals to 0? Right? So the way you determine that is by looking at these two probabilities and then determining which of these two probabilities is larger, right? Now I have explicit expressions for these two. So what I can do is I can just try to find out, right? If I, let's say probability of Y equals to 1 given X is bigger than equal to probability of Y equals to 0 given X, what type of conditions do I get? So let's write that down, pretty straightforward. So I will be predicting output Y hat equals to 1, right? If my probability of Y equals to 1 given X is larger. So this is the inequality that I get. And I can take log both sides, and I can also just substitute the probability expressions, right, here. And if you just argue, I mean, this is fairly straightforward. What you will eventually end up with is this simple condition. So this implies Y hat will be equals to 1 if beta transpose X is bigger than equal to 0. So you get so in your feature space, right? You're basically putting a hyperplane, and then you're saying that on one side of the hyperplane, you're saying you're going to classify as Y equals to 1. On the other side, the class going to classify as Y equals to 0. Okay. So this is, as if you remember this picture that I showed, this is sort of what we wanted, right? So let me quickly then show how do we estimate these parameters. This is where I'm connecting this discussion to the discussion we had last time, right? So now we have a model Y given X, Bernoulli theta X, right? So we come up with a data set to learn these parameters, right? So these are my data samples in the data set. And under our model, I actually already have this probability, right, of Y equals to 1 given X. So now the goal, our first goal will be to come up with a maximum likelihood estimate, right, of these parameters beta that appear now in my distribution. So the first step here would be to basically write the likelihood function, right? So my likelihood function, which is p of y given x beta. So the likelihood function is this. Right. So here, if you think about it, what all I am saying is, right. So if you get, say, a 1 for the first sample, that will come from a coin, right, with parameter theta x1. Right, so that will be theta x1. If I get a 0 for the second sample, the probability of that is 1 minus theta x2. So I'm just multiplying all those, and I've just written this shorthand notation where only one of these two probabilities is going to be relevant for any given term. So when you put yi equals to 1, then this term is going to remain, and this term, the other term, is going to reduce to 1. When I put yi equals to 0, then the first term is going to 1 and the second term remains, right? So this was just a shorthand notation to come up with a form that is easy to work with when I write the log likelihood. Okay, so using this, I can now write the log likelihood for this case, and the log likelihood here, I have just taken the log of the likelihood function that I wrote on the previous slide. So I'm not going to go into a lot of details. I'm just basically substituting all the terms that I know, right? So this goes here, then simplifying, right? So you reduce to this expression log likelihood, and this can be shown to be a concave function in beta. You cannot get a closed form expression for this, but this can be solved pretty efficiently using, for example, gradient descent, right? And since it is concave, you'll have to use either gradient ascent on this or gradient descent on the negative of this. Okay. The obvious next question, right? We know what ML estimator for this case is. Now, can we say something about the map estimator, right? So for map, what we do is we try to maximize the posterior. So I've taken the log of the posterior here, right? And I've written that as log of likelihood plus log of prior, right? Because you had a product inside the log. I just wrote that as a summation. Now, prior, I'm going to just assume that it is Gaussian prior, right? With variance sigma naught squared. So my prior is here, right? And all beta i's are independent. I just make that assumption. I don't want to go into too many details here because I just want to connect this idea to something we discussed last time, right? Because you can work out these details on your own pretty easily. The idea I want to connect is now if you try to find the map estimator, right, which means you are maximizing over your posterior, you get this first term, which is nothing but the log likelihood, which we have already seen, and you get this second term from your prior. And because of the Gaussian assumption of your prior, you basically get this similar term that we also got in regularized linear regression, right? So even in this case, you basically get a regularization term in your map estimator. Okay, so this connection that you can think of regularization as basically putting a prior holds in this case as well. And as I said, that is sort of more generally applicable. You may not be able to visualize that for very, very, very complicated learning algorithms, but still keeping this intuitive idea in mind is also helpful. So we also discussed last time, right? What do we mean by regularization, right? And sort of thought of that as a soft model selection. So you can check that out if you are interested. So I'm not going to go into that again. All right. So let's discuss, right? Can we have nonlinear decision boundaries with logistic regression? Right? We had a similar discussion on sort of this similar discussion related to this, right? When we discussed polynomial regression. We said that you could actually learn polynomial functions with linear regression because linearity is with respect to your coefficients. You could have any types of features that you want, and with the feature augmentation, you could learn nonlinear functions as well. And similar argument holds for the logistic regression as well. Um, since we did not go into an explicit example last time, I thought of including a very quick example so that you guys can visualize how to augment these features. And then I'll just make a very quick remark at the end. Okay, so until now, what we have assumed is, so you have this feature one, let's say, you have feature two, and you have the two types of data points. Let me say this is your first label, this is your second label. So we sort of assume that you have data which is linearly separable, and hence you can have a linear classifier that will separate this data. Now, what happens if you have something like this? Right, so let's say this is your data set. Right? Now, if you're watching this offline later, this would be a good time to just pause the video and think, how would you apply logistic regression to this case, right? So this again is x1, and this is my x2. Okay, so we are going to use that idea of feature augmentation. What I'm going to do is I'm going to come up with some features. So this was the idea, right? Instead of using my original features directly, I'm going to come up with some new features, which will be obtained by this mapping phi, right? So for this specific example, what I'm going to do is I will predict y hat is 1 if minus c, right, which is my bias term, as will be clear now, plus x1 squared plus x2 squared is bigger than equal to 0. This implies x1 squared plus x2 squared is bigger than equal to c. Okay, so what did I do here? So I basically defined two new features. I defined a feature x1 squared, I defined a feature x2 squared, and you get this equation of a circle, and you basically get a circular decision boundary in this case, right? And now if you can even go one step further, and you can sort of make sense of a statement I make towards the very end. You could actually consider this as your one feature, this as your second feature, and try plotting this data. What would this data look like in this sort of new space, right, where I have augmented my features? And you will see that in this space, your data actually becomes linearly separable, right? So you can sort of do linear processing here. Now the point is, right, this is nice, right? This sort of shows how you can use logistic regression, or equivalently, as we saw last time, sort of similar ideas hold for linear regression as well, for the more general cases. But the problem is constructing these features, right? How do I know what feature makes sense? How to augment features? And this is where neural networks have been so useful. So this feature learning or feature augmentation, this is done automatically in a neural network. That's really sort of what it is doing. It is coming up with features that will make your learning process, say, more meaningful or more efficient. Okay. So now, very last topic of this lecture, which is this connection between naive Bayes, and I'm actually going to consider a specific version of that, which is the Gaussian naive Bayes. And Gaussian assumption is going to be very important for what we will be discussing now. And then logistic regression. Okay, we know what naive Bayes is, we know what logistic regression are. I think now at this point, you can probably appreciate why this connection is, I mean, if we do get a connection, why this could be surprising, right? Logistic regression, we just assumed something. We just said, okay, let's just use sigmoid, right? Naive Bayes was coming from this minimization of our expected loss function, which was 0, 1 loss, right? Okay, so here, what I'm going to assume is that we have binary labels, right? Y belonging to 0 to 1. And I have probability of y equals to 1, which is theta, probability of y equals to 0, which is 1 minus theta, because y is binary. Right? So I just have a Bernoulli random variable modeling this. Naive Bayes, we have this assumption that we made in naive. So probability of x given y, right? That is, so your features are conditionally independent given y. Okay, so now the additional assumption we are going to make is that the distribution of the jth feature, which is xj, conditioned on the ith label yi, which is basically one of the terms here, right? Um, it will be modeled as Gaussian. So that is the assumption we make in the Gaussian naive Bayes. So in short, each of these terms will be Gaussian for a given value of y. Okay. So for that, I then say that so here yi will be, so I index I will be using for the outputs, and j will be for the features. So it is Gaussian with mean mu ji and variance sigma j squared. Right? So I just assume that your variance will just depend on the features and not on I, right? And that's sort of to make this, basically to make this connection easily. Okay. All right, I think it might be actually better if I just write this. I think it will have a better continuity, I feel. So let's just write this. So I'm going to now try and derive probability y equals to 1 given x for the model that I have for the naive Bayes, okay? So I have probability just using Bayes rule, and then I have probability of x. And remember, for logistic regression, I know what this expression really is, right? That comes from the sigmoid. Now the question is, can we reduce this to a sigmoid? And that's what we'll try and do. Okay, so now this can be written as probability of x given y equals to 1 times probability of y equals to 1. We do the same thing in the denominator, summation over y, probability of x given y times probability of y. So I wrote the denominator in the same form in terms of the conditional and marginal. Now, in the denominator, I will basically have two terms because I assumed y to be binary, right? So I just have two terms, and one of those two terms will be exactly what I have in the numerator. So this will be 1 over, if I divide and right. So if I bring the numerator to the denominator, so this is what I'll get: 1 plus probability of x given y equals to 0 times probability of y equals to 0. And now this term that I'm going to write in red is what we got from the numerator. Right? So nothing too complicated until now. So now what I'm going to do is I'm going to take the exponential and log of this term that I have in the denominator. Right? So I can equivalently write this. Let me see if I can, let's see if I can move this a little bit here. Okay, so this is my denominator. And I just write this as this. Okay. So I can write this equivalently as x log of this, right? Nothing changed. Now I have this product of two terms in the log. I'm going to write that as summation of logs. So what I get is 1 over 1 plus x log of px given y equals to 0 divided by px given y equals to 1 plus log of py equals to 0 divided by py equals to 1. Okay. And this is where the bracket closes. Okay. So my second term here so this is something I already know. This is just a constant, log of 1 minus theta divided by theta, right? Just probability of y equals to 0 divided by y equals to 1. And now I'm going to start using the assumptions that I have made. Okay, so I'm going to first use the naive Bayes assumption, where I will assume that the conditional of x given y, right? So our x is conditionally independent given y. So I can now write this as log of product j equals to 1 to d, p of xj given y equals to 0 divided by p of xj, y equals to 1, right? So you can sort of start seeing already the connection that I'm trying to develop here. So we already got this 1 over 1 plus x form, right? Which is what we have in logistic regression as well. Okay. So now let me see. Let me now show the slides just to show where we are. So this is the step where I have already reached. Right? So I am now going to look at this term more carefully. I have made only one assumption until now, right? This is where the naive Bayes assumption was made. Note that we have additional assumption, which is the Gaussian assumption as well. And this is what is going to reduce us to the logistic regression form. Okay, so let's look at this term carefully. I'm going to call it tau. Let's add page once again. I am going to look at this term, tau, which is probability xj given y equals to 0 divided by probability xj given y equals to 1, right? So these two are nothing but Gaussian PDFs from our assumption. Right, so this will be x of minus xj minus mu j0 squared divided by 2 times sigma j squared 1 over root 2 pi sigma j squared yeah, I'm just rushing a little bit because I know I will be out of time very soon. So I just want to wrap this argument up before we finish the lecture. Now, this term tau, right, it was sitting inside the log. So if I take log of tau, so first of all, these two cancel, right? So log of tau will give me minus xj minus mu j0 squared divided by 2 times sigma j squared plus xj minus mu j1 squared divided by 2 times sigma j squared, right? Now, if you write a minus b squared as a squared plus b squared minus 2ab, right? Your xj terms are going to cancel because you will have them in both the terms here. So this will reduce to, let me see, this will reduce to 2 times mu j0 minus 2 times mu j1 divided by 2 times sigma j squared times xj plus mu j1 squared minus mu j0 squared divided by 2 times sigma j squared. Right, so this is a constant, right? It doesn't really have this xj factor there. So that's just a constant and will sort of serve as a bias term for us. And now this term is linear in xj. Okay, so if I now show you the final form, right? So you get this linear term in xj, and you get this for all j. You basically have a summation. So you now get, if you define this, right? So this will have to be careful. So I mean, whatever is being multiplied by xj, if I define that as some beta j, it should be actually minus beta j. I'll show that in the slide. You will get this summation or linear combination of xj that we are looking for. Okay, so if you combine all these terms, you can actually write that probability of y equals to 1 given x will have exactly this form. right? Where beta j, xj are the terms that we just saw. There is a bias term, beta 0 multiplied by 1, which will absorb these type of constant terms, right? So what we have shown here is that naive Bayes, right, is basically logistic regression, right? Logistic regression is a little bit more general, but naive Bayes is under these very specific assumptions is logistic regression, or Gaussian naive Bayes, I should say, because Gaussian assumption played a central role. Okay. So this is just an interesting connection, right? So you can recover these forms. For example, if you haven't seen this before, and I introduce this logistic regression with the sigmoid function, it's quite natural to wonder, right? Why sigmoid, right? I mean, isn't there any other function that I can use? And these type of connections start giving intuition why these choices are appropriate. Okay. So I think with this looks like we are close to time already. So let's summarize this lecture and also our second module of the course. We have concluded our discussion on statistical estimation and its role in machine learning. I hope you found it useful, interesting. Sort of depends on if you had seen this already or not. So we focused today on the classification problem, right? So this should be classification, right? And we specifically covered the idea of Bayes classifier, naive Bayes classifier. We introduced logistic regression, introduced its underlying generative model. And at the very end, we also made some connection between Gaussian naive Bayes and logistic regression. Okay, so in the next module, we will start unsupervised learning. So I will see you guys tomorrow. Thank you.